All right, folks, for Unit 3, we're going to focus on polynomial functions. We're going to create polynomial equations and solve polynomial equations, but first we have to focus on graphing these polynomial functions and sort of learning a little bit about what makes a graph look the way it does and how to explore parts of that. So some of this is going to require a graphic calculator. There's going to be some parts that I'll save for the in-class component just so that you all can get some hands-on tactile awesomeness with these graphic calculators, and then we'll kind of fill in some of these gaps when we are in person together, when everyone has their resources. So the goal today is to be able to predict the behavior of polynomial functions, what is happening, what do they look like, and there's some key vocabulary. A lot of this is stuff that you've done before in Algebra 1, so I'll try to jog your memories a little bit. But then there's some parts that are new here, all right? Talking about relative minimum and maximum, and of course our turning points in those graphs. And so reviewing, a polynomial is basically a monomial or the sum of monomials, and you can say, you just use the definition in the definition, so how are you supposed to do that? You can't use the word polynomial or a version of a polynomial in the definition of a polynomial. Say, oh, okay, touche. Well, a monomial is a number, a variable, or the product of a number and a variable, or variables at that point. And so a monomial is basically a single term where you have maybe multiple numbers or multiple variables multiplied together, and it's in its kind of lowest condensed form. This may include exponents, it may include fractions, but you shouldn't have multiple numbers, and you shouldn't have the same variable repeated if it's in its simplified form. We'll chat more about that as needed. The degree of a polynomial is the greatest sum of the exponents of the variables in each monomial in that polynomial. I know that sounds confusing, but we'll show an example a little bit of what I mean by the degree of a polynomial. Essentially, most of the polynomials that we're dealing with are, y equals x to some power, plus or minus x to some other power, et cetera, et cetera. So we're going to look for the greatest exponents. But to be technically clear, it's the sum of all of those exponents is the degree of the monomial, and then the degree of the polynomial is the largest one of those degrees. The standard form of a polynomial is always written with descending order. So the greatest degreed monomial first, followed by the second greatest degreed monomial, et cetera, et cetera, et cetera, in kind of that descending order. We've already done this with quadratics, writing y equals ax squared, that's degree 2, plus bx, that's degree 1, plus c, that's degree 0. And so it's already written in descending order, and we're going to continue that pattern as we deal with cubics and quartics and quintics, et cetera. The lead coefficient is that coefficient of the term with the greatest degree. And so sometimes we read these definitions and we're like, okay, I wrote the things down, but what does that actually mean? And so we're going to explore that a little bit. I'm going to do an example like you would have done in Algebra 1, and then we're going to continue with some tables that we'll explore a little bit in terms of these other scenarios and other situations. So here we have this polynomial. Go ahead and write that down to the best of your ability. And what we're going to do is we're going to understand that this is degree 1, degree 2, degree 0, degree 3, degree 1. I've got two terms that have degree 1, so I'm going to combine those like terms just like we did in Algebra 1. I want this to be my first term because this is degree 3, and that's bigger than 2, it's bigger than 1, it's bigger than 0. And so I'm going to write this in its standard form. It's going to be 2x cubed. I've got 10x's and negative 7x's makes a total of, whoops, that's x's. I need x squareds. Minus 5x squareds. Now I have my 3x's, and then I have 5. This is in descending order, degree 3, degree 2, degree 1, degree 0. All right, there's an invisible 1 here, right? Just like when we have a coefficient of 1, we don't write it. When we have an exponent of 1, we don't write it. Identify the lead coefficient. So the lead term is this right here because this has the greatest degree. So the lead coefficient is 2. The degree of the polynomial is we are going to give this, we're not going to add up all of these, we're just going to take this one right here. This is a degree 3 polynomial. Now we have a special name for that we are going to talk about on the next slide. A degree 3 polynomial, third degree polynomial, we refer to as a cubic polynomial. You might remember that verbiage, that vocabulary from Algebra 1. So if I'm going to name these, classify these using their degrees, using their number of terms, then we can kind of see how this looks like what we did in lesson 9.1 of our Algebra 1 classes. And so name using degree, this is a degree 0, which we call a constant. Degree 1 we call linear. Degree 2 we call quadratic. Degree 3 we call cubic. Degree 4 we call, this is new, quartic. Degree 5 we call quintic. And degree n, we just call it an nth degree. So in this case, I would call this a 9th degree. All right, so these words are new. In Algebra 1, which has been a couple years, you had everything after cubic was just, oh, we just have a 4th degree or a 5th degree polynomial. Now we have vocabulary for that. I don't know why they don't give it to you in Algebra 1. Maybe they just think that you can only learn so many words at a time. But here you're in Algebra 2, you hopefully know these, or at least this has jogged your memory enough. And then these new words, quartic and quintic. By the number of terms, how many terms are there? There is one term there. There are 2 terms here. There's 1 term here, 1, 2, 3 terms, 1, 2 terms, 1, 2, 3, 4 terms. They are separated by a plus sign or a minus sign. 1, 2, 3 terms. So if I'm going to classify these by the number of terms they have, whenever there's 1 term, we refer to that as a monomial. Monomial. All right? Monomial. Sorry for my handwriting. That's what we get. All right. Degree 2, I'm sorry, not degree 2. 2 terms we refer to as a binomial. Binomial. Like a bicycle has 2 wheels. Binomial. When there are 3 terms, you probably know that that is a trinomial. That is, again, not new information, but it maybe has just been a while since you've had to explore that vocabulary. And then when there are 4 terms, we're just going to say it's a polynomial of 4 terms. All right, so if there's 5 terms or 10 terms, we'd say, oh, it's a polynomial of 10 terms, polynomial of 5 terms, polynomial of 8 terms, polynomial of 4 terms. For the other ones, we have specific vocabulary. Hopefully none of that's new, except for these 2. If any of that is new, any of the other things are new, please ask questions if there's something that I didn't explain well enough for you to understand. Come see me, go visit your Algebra 1 teacher. They would love to see you and catch up with you on how awesome Algebra 2 is because of their awesomeness. But obviously, come see me, ask during class when we discuss this. All right, so we're going to write these in their standard form, doing this basic Algebra 1 stuff, combining our like terms. This is going to give us negative 2x's and 5. This is going to give us, we've got 2 cubic terms. We're going to combine those and get 5x cubed. We've got a positive 1x squared and a negative 4x's. There's no constants. I've combined my like terms. That's good stuff. This I need to write in the correct order by switching those. That's a positive 6 minus 2x to the 5th. And so with that, we've got them in their standard form, check. We're going to circle the leading coefficient. So the leading coefficient is negative 2. The leading coefficient is positive 5. The leading coefficient is negative 2. That number that is multiplied by our greatest degree variable. And then classify it by its degree and number of terms. This is degree 1. So we call this, sorry I'm writing in green, I hope that you can read that. That's a linear binomial. I should switch colors. I wonder how well you guys can see that in the video. Oh, you can read that. Linear binomial. This is a trinomial in that there's 3 terms, but it's a degree 3, so we're going to call this a cubic trinomial. This is a 2-term, we call that a binomial, and it's degree 5. We're going to call that a quintic binomial. Using that new vocabulary term, and then hopefully those are other old vocabulary terms. If you have concerns about combining like terms so that we can write in standard form, name them by the degree, name them by the number of terms, please put a comment on Google Classroom or write a note in your notes that you need to ask Mr. Hill about that. End behavior. Okay, this is new stuff. This is new stuff, and this is looking at a graph and determining what the end to the left or to the right, as x goes towards negative infinity, as x goes towards positive infinity, what's happening with the outputs? What's happening to the y values as x goes to the negative or to the positive infinity? So it's usually determined by looking at the degree of the polynomial. You do not have to graph these in order to know what they look like. But initially, we're going to investigate this by graphing them and then taking a look at what that the picture that's painted for us. So here we can see an x squared quadratic, and so we can see that since it's a degree 2, right? So degree 2, it's a quadratic polynomial. We know that it is going to be approaching positive infinity and negative infinity as x goes. It's going to be approaching positive infinity as x goes to the left or to the right. So the end behavior is on the left it goes to positive infinity, on the right it goes to positive infinity. Awesome. The leading coefficient, though, helps determine that as well, because if our lead coefficient is a negative value, then you know that that flips our graph upside down vertically, right? It reflects it over, the x-axis or whatever. And so that means that even though this is a degree 2, it's going to be pointing negative infinity and negative infinity instead of positive infinity and positive infinity. So it's kind of a question of paying attention to both the degree and the lead coefficient. Here, this is the opposite of x cubed, all right? This is y is equal to the opposite of some cubic polynomial. And so it is positive to the left and it's negative to the right, but if we had a positive lead coefficient, this would be facing the other direction, right? It would be reflecting, well, it'd be reflecting over this way, is really how that would go. So it would be going down to the left and up to the right. So we're going to explore that a little bit, but I think it might be wise for us to kind of look at this in terms of, generally speaking, what the sketch of this graph would look like. All right, so if I were to graph that, we would say that to the left, this is as x approaches negative infinity. We're going to say y approaches negative infinity. To the right, all right, that again is as x approaches positive infinity, then y is going to approach positive infinity, all right? This is going to be pointing up on the right, it's going to be pointing down on the left. Over here, y equals 1/2 x squared minus 6. We know what that's going to look like. It's going to look like this picture, maybe a little widened out. We've drafted these already. This is just a sketch, but we can see what's happening at the end. To the left, all right, again, as x approaches negative infinity, we're going to say y approaches positive infinity. To the right end, this side, as x approaches positive infinity, right, y approaches also positive infinity. This is what we refer to as, with degree 1 and degree 2, we can make a prediction, since we have a positive 2 and a positive 1/2, what those pictures will look like without graphing them, and we can predict what is going to happen to the left and to the right. What I would like for you to do in your notes is I would like for you to write these down. Write them down, and then we are going to describe the end behaviors together in class, all right? And so this is going to be a together thing. You are welcome to do these, to try these. I'm not asking you to try these. If these are not done, you don't lose any points for that. If you want to give those a shot to predict what the end behavior is going to be, then please do that. But we are going to go over it in class through some investigation, through some graphing, and then we're going to make this table. So leave this blank. We're going to do this one together also. All right, because what I want for us to do is I want to make sure that we have a good conversation about this. Sometimes there are things that are better done together. So I want to make sure that we get a good chance to look at these situations and use that to sort of make our summary chart for what behaviors we're going to see for an even degree versus an odd degree with a positive coefficient versus a negative coefficient. All right, I want to make sure that we're solid on that. And then we'll talk about this. All right, so go over here to relative minimum and maximum. Now this is new, all right? I did say that this was going to be new, same with that end behavior. And so with respect to relative minimum and relative maximum, I know that this is just vocabulary, and so you can write all that down. But it's the point where the function has the relative minimum has the smallest value over an interval, all right? And as you read the graph from left to right, it's going to change from decreasing to increasing, all right? When it has that valley, you know that you've achieved a minimum value. Even if it's not the lowest of the entire function in the range of the function, we're looking at maybe just a little snippet of the function to try to determine where that relative, or sometimes they use the word local, minimum. Same with maximum. A relative maximum would be, what's the maximum value in this interval? Specifically, we want to look for mountaintops, perhaps. where the graph comes up a little bit and then maybe it dips back down. This would be a maximum. This would be a minimum, relatively speaking. It's not the maximum, right? Because that would be infinity. It's not the minimum, because that would be negative infinity. But there is a relative minimum and a relative maximum in the kind of the local window. And so we want to explore those as best as we can. And that's going to require us to think about the graph. So here, this has an x comma y. Sometimes we care about the specific y value. What's the lowest y value on this interval? Well, what's the x value that goes along with it? So name the point for the relative minimum, name the point for the relative maximum. And sometimes these are not precise, right? They're not exact x comma y's, and so we have to approximate. So here, I want you to write, sketch these as best you can. You're just doing a drawing, so do your best work there. But we're going to approximate these in our graphers. Please write that down. I know that my handwriting is atrocious, but we're going to approximate these locations, these x comma y's, using our grapher calculator. Now, if you want to explore that before coming to class, I want you to press second calc and see if that gives you a little idea of where you would look to calculate the local minimum or maximum value in a function. All right, you can kind of preview that. So try your best to draw those pictures, and you do not have to tell me what those values are. We're going to explore that with our calculators using some of these examples that we're going to do in class. So with respect to finding these relative minima and maxima, we are going to graph these. Then we are going to use the calc menu to identify a minimum, or a maximum. For 3, we're going to round to 3 decimal places. They have a special name for that. We're going to round to the nearest thousandth, all right, which is a hard word to say. So that's what we're going to do, but we're going to do that in our calculators. You are welcome, like I said, to do this if you want to try to do that. But again, my goal is for us to do that in class, to have that be part of our conversation, to springboard the work that we're going to be doing in class together next time. All right. My goal is that you will be able to, by the end of our practice, all right, not the end of the notes, like you can write down the notes and not necessarily understand things, but by the end of our practice, that you would be able to predict the end behavior of polynomial functions.